There does exist a relationship between the electric field and the difference in electric potential between two locations within the electric field. Let us first assume we have an electric field that is constant and uniform everywhere, as shown in this picture. The difference in electric potential between two locations within this electric field could be written as delta V equals negative E times D. Now, there are a few comments I would like to make on this equation. First of all, E is the strength of the electric field. Notice that as we move from our initial location to our final location over a displacement D, the electric field will have the same strength everywhere along that path. That is because we are assuming the electric field to be constant and uniform. Also notice that there is a negative sign in this equation. This negative sign is present because as we move through our displacement D, we are moving from a location of higher potential to a location of lower potential. Therefore, we expect our change in potential, our delta V, to be a negative quantity. Now, this equation does assume that the electric field is constant and uniform everywhere, and you will potentially need to use this equation on homework and exam problems. But you might be wondering, what about electric fields that are not constant and uniform? Is there a way to describe the difference in electric potential between locations in those electric fields? And there is, but in order to do that, we would need to invoke calculus. As I said before, this course is a non-calculus-based physics course, so the material on the previous slide you will potentially need to work with on homework or exam, but the material on this slide you will not see on any homework or exam. So if you are curious, there does exist a more general relationship between electric fields and the difference in electric potential between locations within those electric fields, such as the electric field due to a point charge. That is not a constant and uniform electric field. A more general relationship between these two quantities could be written as this. The upside down triangle with the vector arrow above that is a nabla symbol, and it could be thought of as a spatial derivative that was promoted to a vector. Remember that electric field is a vector quantity. The electric field will have an x, a y, and a z component. Even though the electric potential, V, is not a vector quantity, it still is a function of position. So I could imagine electric potential V as being dependent on the value of x, y, and z at a specific location. The connection between the electric field and the electric potential could be written as this. The x component of the electric field is the negative partial derivative of V with respect to x. The y component of the electric field is negative partial derivative of V with respect to y. And the z component of the electric field is the negative partial derivative of V with respect to z. But again, I want to emphasize the material on this slide will not be on any homework or exam, as this is a non-calculus based physics course. In this next example, we are told that there is a sphere made of some conducting material such as a metal. We are told that this sphere is 4 meters in radius and has an excess of 10 coulombs of charge placed on it, and we're asked to investigate the electric potential inside the sphere. Before we actually perform any calculation in this example, we first need to make a few claims. The first claim I want to make is that the electric potential at all points outside the sphere, in other words, the electric potential at all points that are a distance greater than 4 meters from the center of the sphere, will look identical to the electric potential due to a 10 coulomb point charge that could be found at the center of the sphere. So I could, in principle, for all points outside of the sphere, pretend that the sphere is replaced by a single point charge of 10 coulombs. Now, this seems like a reasonable expectation to make, but we're not allowed to just go around making claims. We need to be able to justify those claims. So how could I justify making this substitution? In order to argue this, let's think back to the previous chapter where we discussed Gauss's law. Let us imagine that there is a spherical Gaussian surface centered on this sphere, and let's have this Gaussian surface be slightly bigger than the sphere itself. So this Gaussian surface will be a sphere of radius slightly more than 4 meters. Here is that spherical Gaussian surface. Let us place an identical Gaussian surface centered on this point charge. So here is another Gaussian surface of radius slightly bigger than 4 meters centered on this point charge. If I think about how I expect the electric field created by the charge, or all these charges, to look as it passes through this spherical Gaussian surface, I expect the electric field through this Gaussian surface to be evenly distributed over the entire surface. And that's because this is a highly symmetric scenario. I have the point charge at the center of a sphere. So I expect the electric field to be uniform and perpendicular to the surface at every location. Similarly, I expect the electric field passing through this Gaussian surface to be uniform and perpendicular through the surface at every location on the surface. So essentially I am saying that the electric field through these two surfaces should look identical to each other. Remember that we are dealing with a sphere. We are assuming that this sphere is perfectly smooth, and because the sphere is perfectly smooth, all the excess charge is going to reside on the surface of that sphere. We learned that in the previous chapter. And therefore, all these excess 10 coulombs of charge should spread out evenly over the entire surface, giving me a nice, even electric field over the entire surface. Okay, we talked about the electric field through the surface, but what about the electric potential? That's what we're really interested in here. Remember that electric potential is connected to the electric field, and the way they are connected is I could write E is equal to negative nabla V. This equation is just shorthand. I could write the components of the electric field as Ex is equal to negative partial derivative of potential with respect to x. The y component of the electric field is negative partial derivative of electric potential with respect to position y. And the z component of the electric field is negative partial derivative of v with respect to z. Now don't worry, we're not going to use too much calculus in this derivation. Let's think about what we have here. If the electric fields look identical at all points outside the sphere, then at least up to a constant, the electric potential will need to be identical in both cases. We know that the electric potential due to a point charge could be written as V is equal to KQ over R. And if I take the partial derivative of V with respect to x, y, and z at any point in the universe more than 4 meters away from this point charge, I would have the electric field at that corresponding point. Now, if I were to write the electric potential due to this sphere of charge in a very similar way, I could write V is equal to KQ over R plus a constant. When I take these derivatives, the constant term will just go away, and then I will get the correct electric field at any point I want in the universe outside of this sphere. So, up to at least a constant, the electric potential should look identical. Now, let's think about this constant for a moment. What do we want to do with it? Well, we would like to say that if you are infinitely far away from a charged object, that charged object should not be able to affect you. So we have a certain degree of freedom, and we could choose that if you are infinitely away from a charged object, the electric potential due to that object should be equal to 0. So I could imagine that if I send R to infinity, This term kq over r will fall away to 0, and I'm left with just this constant. But I want the electric potential infinitely far away from my charged sphere to be 0. And the only way I could do that is to have this constant c be equal to 0. Okay, so at points outside the sphere, the electric potential is identical to a point charge with the same total amount of charge located at the center of the sphere. So if I were to plot v as a function of r being the distance away from the sphere, we have the same v equals kq over r. So here is r equals 4 meters right here, and v equals kq over r. We'll have that 1 over r behavior that looks something like this. We did not yet talk about the inside of the sphere. Now, if you think back to the previous chapter, we also said that at points inside a conductor, the electric field is going to be 0. So I could say for points r is less than 4 meters, for points inside the sphere, the electric field is going to be equal to 0. How do I make the electric field 0? Well, I need to have these terms equal 0 for all points inside the conductor. And the only way I could do that is if v is a constant. So requiring that E is equal to 0 implies that inside v is constant. At this point, we are nearly done with this question. We just have to figure out what is the value of the potential inside the conductor. Because if I want, I could say maybe this is v equals constant, or this is v equals constant. All of these are different choices for v equals constant. How do I choose which of these choices is the correct value for the potential inside the conductor? In order to answer that question, we are going to make another requirement. We will require that the electric field is never infinitely large in this problem. In physics, we don't really like infinities. So let's think about what the electric field might look like as we pass from the inside of the conductor to the outside of the conductor. So here is the side of my conductor, and we are walking from the inside. At every step along this path, we measure the value of the electric potential. We get the same constant value, but then we step outside the conductor and we see the electric potential decrease as kq over r. Now, we said we do not want the electric field to be infinitely large anywhere throughout this path. That would be bad. So what would it take to measure an infinitely large electric field? Let's consider this plot. Let's assume that here is the value of the electric potential versus distance away from the center, and outside at distances greater than 4 meters away from the center of the sphere, we have that kq over r behavior. But then here is the surface of the sphere at a radius 4 meters. And let us suppose that the electric potential has this value inside the sphere. Let's think about what this would really imply. Notice that there is a discontinuity in the value of the electric potential between the inside and the outside of the sphere. This is going to be very important. I could imagine that if I am walking from the inside of the sphere to the outside of the sphere, I take a number of steps, and the step that I take in going from the inside to the outside will have a certain length. Let's call the length of my step delta x. If I were to draw the step on this plot, I could say that the length of that step delta x would be something like this. So here is my step delta x. Now we could ask, what is the change in potential across that step? I would say I began inside the sphere, so the value of my potential was this value. I ended outside the sphere, so the value of my potential was here. So the change in potential as I made this step was delta V. Looking at these equations, the relationship between the electric field and the electric potential tells me that I could make a pretty good approximation for the strength of the electric field by saying E is equal to delta V over delta X. Now, I am allowed to take as small of a step as I want. I could go right to the edge of the sphere, then take a teeny tiny step to get outside the sphere. In other words, I could make delta X arbitrarily small. As I make delta X smaller and smaller, delta V is still going to be a finite value. And based on how this plot is drawn, in the limit where delta X becomes infinitesimally small, in the limit where delta X goes to 0, delta V is still going to be this finite number. So the strength of the electric field would effectively become whatever this change in electric potential, whatever the finite value of delta V is, divided by 0, and then the strength of the electric field at the surface of the sphere would blow up to infinity. And we don't want this. The only way that we could avoid having an infinitely large electric field at the surface of the sphere is if the value of the electric potential inside the sphere matches the value of the electric potential outside the sphere at the surface of the sphere. So the electric potential plotted as a function of distance from the center of the sphere must look something like this. Now we are ready to perform a calculation that allows us to determine the value of the electric potential inside the sphere. I know that the electric potential inside the sphere has to be the same as the electric potential just barely greater than 4 meters away from the center of the sphere. And based on arguments we presented previously, we could say the electric potential outside the sphere is identical to the electric potential from a point particle located at the center of the sphere. So I could say V is equal to KQ over R. So K is Coulomb's constant, 9 times 10 to the 9. We'll place a 10 Coulomb point charge at the center of the sphere, and we're going to consider a point 4 meters away from the center of the sphere. And when I put these numbers in a calculator, I find the potential is going to be 2.25 times 10 to the 10 volts. So the electric potential inside the sphere will be a constant 2.25 times 10 to the 10 volts everywhere inside the sphere.